Okay, cool. So Dr. C sent me some problems to go over with you guys. I'm gonna just go ahead and do that. So the first one is you have a system with a wave function. You have these two. So I'm just gonna say that the full wave function is gonna be the addition of those two. So x plus a, I need a bit more space. O minus x. And then it's saying all these little specifications about the wave function. Draw a picture of the wave function. All right, we'll do that in blue. So we're looking in a box. So first we have to do our little box. And then we're gonna look at what the specifics of this box are. So we see here that v is equal to infinity everywhere else. So on either side of the box, we're gonna do v equals to infinity. And then it says v is equal to 0 for 0 to, okay, between 0 and L over 2. So that's probably going to be inside the box. But let's look up here first. These are specifics for our wave function. So as we can see, it goes from 0 to L over 2, then L over 2 to L. So then I'm going to go 0 to L over 2 to L as being our section inside the box. And then on this side, I'm going to do v is equal to 0 because that's what this says here, from 0 to L over 2. And then we can assign these wave functions because for the 0 to L over 2, we had the wave function equals ax. And then for the L over 2 to L, we had a L minus x. So now in order to graph this, you could kind of guess like, okay, this is ax, probably gonna be positive, something like that. And this one's L minus x, that's gonna be some slope. I always have some trouble like imagining that. So what I used to do is I used to just like max them in. So do the minimum x and the max x and just kind of plug it in. Right, because we have these bounds, we can do that. So our minimum x is 0. So a 0, so to 0. Then our maximum is L over 2. So a L over 2 equals to a L over 2. I know it seems kind of redundant. It made me feel more comfortable when I was taking this class. So then we're gonna do the next one. We see our x minimum for this one is L over 2. So a L minus L over 2. That's gonna probably get us L minus L over 2. Positive L over 2. So that's again gonna be a L over 2, which is awesome because that means that at this L over 2 spot here, we have a peak up here, or it's probably gonna be a peak of a L over 2. You probably don't have to write that, but you can just note it. I'd actually probably write it closer to the dot. And then for our maximum x, we have a L minus L, which is going to be equal to 0. Right, so then it's going to go from 0 up to there, and then on this side from 0 up to there. So that would be how I draw. Oh, Hazel's here. Is there anyone else I missed? Welcome, Hazel. Let me go through this real quick since you haven't really missed out on much so far. So basically we had, we suppose the system was a wave function. We had to draw a picture in a one-dimensional box. Let me get rid of some of these scribbles. And then we have these two wave functions. So what we did is we went, okay, 0 to L over 2, that's this part here. And then L over 2 to L, that's this part here, which means that's our wave function for that section, and that's our wave function for that section. And then what I did is I just did the min and max of the x's. So like for this one, the minimum x is 0, which is gonna get you 0. Then our maximum x for that section is L over 2, which gets us AL over 2. So then you can draw this part here. And then for the second part, we have the A L minus X wave function, where we plug in the minimum X of L over 2 and gets us AL over 2, which is nice because we have the same meeting spot. And then our maximum is L, so we go ahead and plug that in for X, and we get 0, which means that this is going to go downwards. And then we also noted that, where is it? Here. V is equal to X for 0 to L over 2. So we have V is equal to X on this side of the box. And then Vx equals infinity everywhere else. So that's why we have these written here. Yeah. And that's just me calculating. Okay. Anyways, the next part asks us to set up, but don't evaluate the integral with the limits. So we know that we have a wave function here. We combine them into this wave function here. Let me switch colors. Normalization constant. Okay. Right? And we know that in order to normalize, we do the integral of these two dx, right? However, we can't just combine them together, which that's kind of the same as square dx. And because we're normalizing, it's going to be times the normalization factor is equal to 1. But anyway, because we have these two separate like regions, we need to separate it into two kind of integrals. So the way that's going to look is we're going to have our 1 is equal to normalization function for the first one. The normalization should be the same for for both. So you're going to eventually factor it out, but I'm just going to write it as is, just so we can see how it moves. And then we have our wave function, which is our AX. Because we're doing this wave function times the anti-wave function, but it's not really, we just kind of multiply by itself because we're not at that level where we need to do antis, thankfully. And then times dx. And then this is a part that you will almost definitely be checking for. So I'll write it in red. She wants you to write your limits here. So your limit 0 and L over 2, because that's not look like a 2. Because that's this part here. And that's how you're notating it into the wave function. Anyway, from there you can add the second part, which is going to be again the normalization factor, wave function, integral of the wave function, this time the A L minus x1. You could probably square it like that, just because it means the same thing. I'll just keep it consistent, because why not? And then again, you got to make sure you put your limits on this integral. So for this one, it's L over 2 and L. With limits, always your lower at the bottom and upper at the top. My twos are looking wonky today. L over 2. Okay. Now, I'm not sure if this is how she meant you to just set it up, or if she means you to like simplify it as far as you can. Just to be safe, I'm gonna simplify it. So let me add a page. Just because I don't think we're gonna have enough room on that. And then let's copy this. Okay. Erase this upper limit, lower limit notes. So obviously the first thing you're going to be able to do is kind of factor out these ends as well as the A's, but we can do those later because they're not in a format that automatically makes you think you can factor them out. So we'll also condense these. 2n squared, 0 a squared, x squared, right? Because they're multiplied against each other, dx plus the integral of L2 over L, a squared, and then L minus x squared, right? Because that's going to go there. No, yeah, it's not added or anything. So it's just multiplied against each other. Because you can also think of it going like this. L minus x minus a L minus x becomes a L minus x squared, and then you bring in the squared for both. X squared. Cool. Dx. And so then from here, now you can see that, like, oh yeah, I can factor out that a too. So you can go ahead and do that. So 1 is equal to n squared, a squared, integral 0, L minus 2. Make sure you're keeping that limit, your limits on your integral. She almost definitely will be checking for that on this type of problem. It's not going to lose you a ton of points, granted, but it's still nice to be able to not lose points if you don't need to. Dx. And then from here, I'd honestly leave it because anything further and then you'd be trying to integrate it. And I think she said, do not evaluate the integral. So yeah, I'd probably leave it there. Or I guess you could divide that over that way, but yeah, we can check the key right now. Okay. Oh yeah, she left it right there. She left it where we left it. Cool. And then her box looks very similar to ours. The only difference is she didn't write the AL over 2 here. So nice. Yeah, and then she also wrote the limits, so she keep those. I'll just put a 1 up here. Cool. And then it asks C, why do you need the wave function to be normalized? So what do you guys think? Why would we need to normalize the wave function? Alrighties. Okay. Oh, nice. Yeah, that's exactly right, Monica. you have to be able to find the particle. So by normalizing the wave function, you're kind of mathematically trapping your particle in the box. So you know that it's in the box. You don't know where in the box, but you know it is in the box. So yeah. So which means the probability of finding your particle in the box is 1. Good job. Because yeah, remember this is also our probability equation. Nice. Number 2, do some research and use your own words. I haven't really, we can say this one for last. I haven't really looked into it that much. I do know that the Heisenberg uncertainty principle is kind of like what you think about electrons, where you can't know position and speed at the same time. Although I think the technical term would be momentum. So can't know a same time. And then we're looking specifically at wave function, particles that act like a wave. And then we'll look into the history and stuff later. We'll come back to that one. Okay. So then this third one is talking about a linear polyethylene that you consider a particle in a 1D box. It says carotene has 22 conjugated carbon atoms, internucleon distance of 140 probably picometers. Okay, each state up to N11 is occupied by 2 electrons. Right, so that means that you have like these little diagrams, right? This is 1, or I guess that's 11. This is 1. That means that all of them are occupied up to 11. And then in the first excited state, in which 1 electron occupies the N equals 12. So for 12, we have the first time that we only have 1 electron. Which means that these are 2 going to be like our energy levels. So it's going to be 11. That looks like a V. And this is going to be E12. Okay, there we go. What is it asking for? Separation and energy. I would probably approach this using, I know there's an equation that calculates like the network length. I believe that equation should have energy. Let me, oop, let me, Okay, yeah. So we use our network length calculator probably. A is equal to square root of n squared f, or I guess it's nf squared minus ni squared. I'll keep the notation the same between the two. And then h squared. H should just be a constant. Oh, right. The reason we were able to take out a here is because it was a constant. Although you guys probably knew that. I'm just, yeah. Over the delta E. And then what we're going to want to do with this is isolate for E. Where I believe the E is probably going to be something like E12 minus E11. Would that be correct? I feel like that would be correct because it's like the higher and lower. So we would need to isolate this out and then see how it looks from there. So I'm gonna do this in the other paper just because it'll help. Let's get the circle one. And then this is for number 3. Cool. So first things first, we're gonna go squared to get rid of that square root, which that's gonna give us little a squared is equal to squared minus ni squared h squared. Probably move this denominator over to the side, which would get us, I'm going to copy and paste because that's easier. Except I'm going to get rid of some of these lines. I need to parentheses. Equal to our numerator. From there, I would probably, oh shoot, I used the school account and it's gonna be cutting my meeting off because the school no longer has Zoom Pro. So, we still have 10 minutes. I'm gonna try and finish this problem in that time, and if I don't, then just rejoin the same Zoom link. Okay. Anyway, divide by h2. I don't know if I want to get rid of that NF, move it over yet or not. I mean, yeah, we're isolating for E, so. So then it would probably be better then if we're isolating for E. Is dividing this by a squared, 8, and m. And keep those in that order. Right, because in that way you get rid of these three. And then you isolate for E. I'm gonna write it this way, NF squared minus NI squared times H squared over 8A squared M. Because then this is gonna be our final, which was our highest, which I believe was 12. Wrong way. Yeah. Our high state, it was 12, so and final is equal to 12, and then our low state was 11, so Ni is equal to 11. So then we can go ahead and know that that's going to be 12 and that's going to be 11. I don't know how much longer we have on the Zoom. We'll just leave it at there for now. Also, because we've already got this 12 and 11, this is the delta E. So this is what we're solving for. So we don't really need that. Oh. And I'll pause here, let the recording. Yeah, we'll let the meeting end and then we'll regroup and we'll plug things in after we regroup. Sounds good? Cool. See you guys soon.